Okay? So for chlorine, chlorine has its valence electrons in the 3s and the 3p. 2 in the 3s and 5 in the 3p. 7 electrons gives us 14 total. Sigma 3s, 1, 2. Sigma star 3s, 3, 4. Sigma 3p, 5, 6. Pi 3p, 7, 8, 9, 10. Pi star 3p, 11, 12, 13, 14. Then, to calculate the bond order, we look at the bonding electrons. 2, 4, 6, 8, minus the anti-bonding electrons. 2, 4, 6, divided by 2 gives us a bond order of 1. So that's what I'll expect you to be able to do on the test. Draw a molecular orbital diagram for whatever. Now, what if this was a heteronuclear molecule? What if it was carbon monoxide? What would you do?
Cry.
Not cry. You do the same thing on the second energy level. You'd put carbon on one side with its 4 electrons and oxygen on the other side with its 6. What if it was a cyanide ion? Carbon on one side, nitrogen on the other side, and because it's an ion, what do you need to do? A negative ion? Add 1 electron. Which side would you add it to?
Carbon.
I'd put it on nitrogen because it's a more electronegative element. But does it really matter? No. It just matters in the middle. I would just always add an electron to the more electronegative element.
Here, do you need this?
Why would you do that?
Well, these don't just fall anything.
Yes. The only ones that
So,
aren't for-
we've looked at drawing these diagrams, and we saw the first advantage of molecular orbital theory. It explains the paramagnetic behavior of diatomic oxygen. It's the only theory that can explain that, why oxygen is attracted to a magnet. The other thing that we have in the carbon is that we can explain things that we can't explain very well in valence bond theory. And the example of this is the carbonate ion. Carbonate has 3 resonance structures. We've drawn this over and over in valence bond theory. Carbon has 3 oxygens attached, and we can draw 1 double bond and 2 single bonds. But this doesn't really fit with what we observed. So we came up with this crazy idea of resonance, saying, well, we can't draw a Lewis structure. It's something in between all of these that are equivalent. And then we would go ahead anyway in valence bond theory and say, well, the carbon has a sigma and a pi bond to one oxygen and sigmas to the other, but that really doesn't explain it. It does a poor job. So in the MO theory, we suggest that we have molecular orbitals forming and we don't need any bonds. Reagan?
Can we like turn off the lights? Because when you're writing, it's hard to see. Like I don't know what light.
Better?
Hopefully.
So in MO theory, we don't try and draw Lewis structures. We just say, well, I have carbon, I have 3 nuclei for oxygen around it, and then this encompasses all of the nuclei. And we have orbitals that belong to the molecule encompassing the nuclei, and we call this delocalized bonding. So, molecular orbital theory says that the formation of molecular orbitals allows delocalized bonding. The electrons don't have to stay between any 2 nuclei, they just have to stay within the confines of the molecule. And so that makes a lot of sense, and it gets rid of the need for resonance structures.